All right, let's look at an application problem. So, this is a circuit problem, so of course this is I like this. But even if you don't know anything about circuits, um, I mean, essentially all you're given is some information and a differential equation to solve. So you don't have to know anything about circuits, but it's good to know that these have tremendous real life applications, not just circuits, but all over the place. So, so we're given this circuit, and the switch is closed at time t equals 0, which essentially creates a step function. The voltage across the circuit goes from 0 to and steps up to 40 volts. Okay, and so and we're given the values of the inductance and the resistance. And so all we really need to do is plug in those values. So L, we're told over here on the circuit and in the description of the problem is 2. So we have 2 di dt, all right? So I is the current, and is equal to R, which is 10 ohms, I. So I is our variable. That's what we're trying to solve for, trying to figure out what the current is in this circuit. And the voltage is just 40 volts, okay? So, and it's just a step function. The switch, you know, and then initially it's open, the switch is closed, and then the voltage goes straight to 40 volts. All right, so now we just need to solve this, right? So let's rearrange it a little bit. We can rearrange this into di dt is equal to, now I can basically subtract 10i from both sides and then divide both sides by 2. Okay, so I'm going to do that as one step. So I'm going to get 20 minus 5i. Okay, so now it's looking a little bit more like something we can solve. One tip, it's not, you know, it's not a hard and fast rule, but one tip is that I tend to like to work with positive coefficients on the variable. So here we have a minus 5. It's just much easier sometimes if you have a positive, especially a positive 1 coefficient. So I'm going to actually factor out a minus 5. Okay, that's just kind of from my experience what makes it easier. Okay, if you don't do that, it's okay. You can do it. It just makes it slightly easier. So I'm going to get minus 4 plus I. So that gives me a positive 1 coefficient on the I. And it just makes it a little easier. And the reason is I don't have to do any kind of U substitution and keep track of a lot of constants when I integrate. So let me show you what I mean. So now that we have this rearranged, now I can write this as 1 over, I'm just going to change these around, so it's I minus 4 di, okay? And then on the other side, I'm going to have minus 5 dt. All right, and then I can integrate both sides. Now you can see now I just have a positive 1 coefficient on the I, so it makes it easy just to write this as this is the natural log of I minus 4. Okay, and I don't have to worry about doing any kind of U substitution and keeping track of coefficients. So, and then on the other side, what I end up is a minus 5t plus a c plus a constant. All right, now I can basically E, right? I can just do this so that I can isolate the I minus 4, right? Still absolute value, is equal to e to the minus 5t plus c, which I can actually write as e to the c times e to the minus 5t. Okay, e to the c is just a constant. I can get rid of the absolute value sign just by just making that e to the c an arbitrary constant that can be positive or negative. So I get I minus 4 is equal to a, let's call it a, e to the minus 5t. Okay, and now I can, let me write it over here, solve for I. So I is equal to 4 plus a e to the minus 5t. Okay, so that's my general solution, but now I know that when I is 0 when the circuit is first closed at t equals 0. So I have this initial condition where I is equal to 0, when t is equal to 0. So I'm just going to substitute that in. So e to the 0 is 1, so that's telling me that a is equal to minus 4. And now my particular solution for the current in this circuit is 4 minus 4 e to the minus 5t. Okay. Now I'm asked to find the current at 0.1 seconds as well. Okay, so now that I have a function for the current in terms of time, I can just substitute 0.1 for t, and that'll give me 4 minus 4e to the minus 0.5. I'll put that in my calculator, and what I end up getting is 1.57 amps. Okay, amperes. All right, so that's my solution, and here's my particular solution for this problem as well. All right, so that's all I have for the examples in this section, and you are ready to start the discussion questions. I will see you in class.